All right, the last time we talked, we got up through the Bohr model of the atom. We talked about how his atom explained electron orbits beautifully, but only for hydrogen. His model did not explain any other elements on the periodic table and the wavelengths of light that their electrons emitted. So we had to come up with a better model of the atom. And that brings us to the modern quantum model of the atom. So the first step in developing the quantum model is that de Broglie determined that an electron could be both a wave and a particle. Remember, we already determined from Planck and Einstein that light could be both a wave and a particle. But now de Broglie is applying that wave-particle theory of light. He's applying it to electrons. In fact, he applied it to all matter. He was a mathematician, so this is a mathematical model, but his mathematical model worked. So all matter can behave as both a wave or a particle. An electron has mass, so it's definitely a particle. Remember, an electron has mass. It's very small, but it does have mass. But the quantized electron orbits that Bohr modeled were consistent with wave behavior. Remember, Bohr had these wavelengths of light that corresponded to specific energy transitions of the electrons. So de Broglie recognized that we had particle properties and wave properties of electrons. So what evidence did de Broglie have that electrons could even be like a wave at all? That evidence came from diffraction patterns and interference patterns. Diffraction is the bending of a wave as it passes by the edge of an object. So if you have particles, if electrons are truly just particles, then if you have a screen with two slits in it and you let the particles pass through it at high speed, those particles should, on the optical detecting screen, just appear in two bands of lines as they pass straight through those slits. That's particle behavior. But if electrons actually behave as a wave, then when electrons pass through those slits, those waves can actually bend as they pass by the edge of the slits in the screen. And this is in fact what you see with electrons. Instead of just having two beams detected by the optical screen, you have multiple beams detected by the optical screen as electrons pass through. The other set of evidence that supports the wave behavior of an electron are interference patterns. So when two waves collide, when two waves overlap with each other, you can have two things happen. Either the waves kind of add up, making a bigger wave, or the waves can cancel each other out, and you have a decrease in energy. So waves that combine can either cause an increase or a decrease in energy. And here is that interference pattern that we talked about, that light, which we know behaves as a wave as well as a particle. Electrons show a similar interference pattern where sometimes waves cancel out and sometimes waves add to each other and have an even bigger signal. So this brings us to Schrodinger's wave equation. Schrodinger created a wave equation that described the wave properties of electrons mathematically. You do not need to know Schrodinger's wave equation. I just have it for you here if you're curious what it looks like. But his wave equation is the basis for the quantum mechanical model that we have today for electrons. Basically, what he is responsible for is he defines the probability of finding an electron at a given place around the nucleus. He said that electrons do not travel around the nucleus in a neat fixed orbit like planets around the sun, so we're not going with Bohr's model anymore. Instead, he says that electrons exist in orbitals. And an orbital is a three-dimensional region, not a kind of two-dimensional orbit, but a three-dimensional region or cloud around the nucleus where you have a probability of finding an electron. Okay, so there's this whole cloud here, and we have a 90% probability of finding the electron inside this sphere. Can the electron be outside that sphere? Yes, it can. There's a 10% chance that it's not inside that sphere. But we have these shaped, 3D shape orbitals that determine the likelihood of finding an electron in a particular area. We'll find that these orbitals can have different shapes. Some orbitals are sphere-shaped. Other orbitals have this kind of dumbbell shape. So, with Schrodinger's wave equation, we have a finite number of solutions for locating electrons. He specified 4 quantum numbers to give us the address, kind of the location of any particular electron in an atom. And you can kind of think of this as being a ticket to a sports event or to a concert, where maybe you're told that you are in the if your ticket starts with a 100, then you know you're on the ground floor. If it starts at a 200, you're in the middle floor. If it's a 300, you started in the top floor. Then if the second digit of your number is a 4, then you're sitting here on maybe the north end of the arena. If the second number is a 2, then maybe you're sitting here at the south end of the arena. Then the last digit kind of specifies where exactly you are, like this is 142 versus 143 versus 144. And then you'll have an actual seat number within that section. Now, no 2 electrons can have the exact same address, just like no 2 people for a sporting event should have the exact same ticket. They each have a different seat. Even if they're sitting in the exact same section, 142, they're sitting in a different row and a different seat. I'm going to give you more information on these quantum numbers later. Before we talk about those quantum numbers, let's talk about one more scientist and his contribution to the quantum mechanical model of the atom. Schrodinger, with his wave equation, really came up with a quantum mechanical model, but Heisenberg refined it. He added to the quantum mechanical model with his uncertainty principle. He said that it was impossible to know both the velocity and the position of an electron at the same time. If you measure one thing, you actually, in the process of measuring it, change the other thing. So if you measure the velocity, then you change its position. Or if you measure its position, you've changed its velocity. All right. So those are all of the scientists involved in coming up with the modern quantum mechanical model that we have for the atom today. So let's look at a little bit more detail about the quantum mechanical model and these 4 quantum numbers that determine the location of an atom. The first quantum number that you need to know about is the principal quantum number, and the abbreviation for the principal quantum number is the letter N. It specifies the main energy level. And with the main energy levels, as the energy levels get further out, then the size of the orbital increases. So your average distance from the nucleus increases. If you're in the 3rd energy level, you're further from the nucleus than if you're in the 1st energy level. Also, as you get further from the nucleus, those electrons also have higher energy. So the energy of the electrons increases as you move further from the nucleus. The principal energy levels can only be whole number integers. So you can have the 1st energy level, the 2nd energy level, 3rd, 4th, 5th, 6th, 7th. It has to be a whole number integer. That's the first quantum number. The second quantum number is called the angular momentum quantum number, and it's symbolized by the letter L for angular with the L. And it specifies the energy sublevel. And we'll learn more about these later, but a sublevel, the sublevels are S, P, D, and F. They have those names, and those names correspond to different shapes of orbitals. So the S orbital is spherical in shape. The P orbital kind of has this dumbbell shape. A D orbital can have a cloverleaf shape or some more complicated shapes, and F orbitals get very complicated in shape. L can be an integer between 0 and n minus 1. So n, remember, was the principal quantum number. So the numbers that correspond to these orbitals are, when L equals 0, that's an S orbital. When L equals 1, that's a P orbital. When L equals 2, it's a D orbital, and when L equals 3, it's an F orbital. These sublevel shape names are important. You do need to know the sublevel shapes, so please label them in your notes. You need to know the names S, P, D, and F, and you need to know the shapes for S and P orbitals. You do not need to be able to draw D and F orbitals. So we have the sphere shape for S and the dumbbell shape for P. The third quantum number you need to know about is the magnetic quantum number. And magnetic is represented by the letter M. And this specifies the exact orientation of an orbital around the nucleus. So orbitals can have the same shape but different positions in space around the nucleus. But those orbitals combine together to form a spherical shape. So for instance, with the dumbbell-shaped p orbitals, you can have a p orbital that's along the x-axis, and a p orbital that's along the y-axis, and a p orbital that's around the z-axis. So 3 different orientations for the p orb sublevel. P sublevel has 3 orientations. And those roughly add up together to form a sphere. So the shape of an atom is still approximately spherical when you add together all of these probability regions of where you would find an electron. Why are there 3 orientations for this p sublevel? Well, that is because the values of m are integers between negative L and positive L. So the p sublevel, remember, was represented by an L value of 1. And the values for m range between negative L and positive L. So in this case, it would be -1, 0, and +1. That's 1, 2, 3 different orientations for the p sublevel. So what this means is each type of orbital, S, P, D, or F, has a fixed number of different orientations. S orbitals always have just 1 orientation. P orbitals always have 3 orientations, as we saw in the previous slide. D orbitals can have 5 different orientations in space, and F orbitals can have 7 different orientations in space. Here are pictures of those different orientations. The sphere is easiest to visualize. The P is also reasonably straightforward to visualize with its 3 different orientations. D and F orbitals get a little more complicated, but you can see that we have 5 orientations of D orbitals and 7 orientations of the F orbitals. The 4th quantum number and the final quantum number that you need to know about is the spin quantum number, S for spin. This number specifies the spin on an electron. The spin on the electron can be +1/2 or -1/2. It doesn't depend on any of the other quantum numbers. So each orbital orientation can hold 2 electrons, but those 2 electrons cannot have the same spin. They must have opposite spins. So since each orbital can hold 2 electrons, that means since the s sublevel has only one orbital orientation, the s sublevel can hold 2 electrons. The p sublevel has 3 orbital orientations, so the p sublevel holds 2 times 3, or 6 electrons. The d sublevel has 5 different orientations, so the d sublevel holds 2 times 5, which is 10 electrons. And the f sublevel has 7 different orientations, and so 2 times 7 is 14. The f sublevel can hold 14 electrons. This looks like a lot of different numbers to memorize, but these pieces of information, the number of electrons in each sublevel, can actually be derived from the structure of the periodic table. And you're allowed to have a periodic table on your test. So using the periodic table to kind of help you remember that S sublevels have 2 electrons, P sublevels have 6 electrons, can help you reduce the amount of memorization you need to do. The Pauli exclusion principle. The Pauli exclusion principle states that no 2 electrons in an atom can have the same 4 quantum numbers. This is related to that kind of address thing that we talked before. So we're kind of summarizing all of the rules here. Each electron has a unique address, and that address is specified by our 4 quantum numbers: the principal quantum number n, the angular momentum quantum number L, the magnetic quantum number m, and the spin quantum number s. Remember, the principal quantum number tells you the main energy level. The angular momentum quantum number tells you the energy sublevel, the shape, whether it's S, P, D, or F. The magnetic quantum number tells you the orbital orientation. So remember, S has 1 orientation, P has 3, D has 5, F has 7. And the electron spin, an electron can either have a spin of positive a half or negative a half. So summarizing what we know about quantum numbers. The quantum number m, the magnetic quantum number, which determines the orientations, that depends on L, the energy sublevel. And L in turn depends on n, the main energy level. So m depends on L depends on n. Quantum number s does not depend on anything. So it doesn't matter what energy level you're in, or what sublevel you're in, or what orbital orientation you're in. You can always have 2 electrons per orbital. However, because m depends on L and L depends on n, we can see that the main energy level, energy level 1, can only have 1 sublevel and therefore only 1 orbital orientation. If you're in the second main energy level, you can have S or P sublevels. And because it's a P sublevel, the P has 3 different orientations. So the first energy level can only hold 2 electrons total, but the second energy level can hold 8 electrons total. The third energy level has S, P, and D orbital sublevels. And S can still only have 1 orbital orientation, but P can have 3 and D can have 5. So when you take all of those into consideration, you can have 18 electrons in your third energy level. Following the same logic, you can see that the fourth energy level can have up to 32 electrons in it. In the next module, we're going to determine electron configurations for atoms using this, based off of these configurations. These configurations are based off of the quantum mechanical model and knowing how many electrons can exist in each of the different orbitals, sublevels, and energy levels. I hope this helped.